Okay, this is section 8-4, the normal distribution. Our objectives are to calculate the z-scores for a data point and to convert a z-score to a percent using the normal distribution. Characteristics of the normal distribution are that it is bell-shaped, has only one mode at the center, and is symmetrical. The mean, median, and mode are all the same. The total area under the curve is equal to 1. And recall that 1 is the decimal representation for 100%, meaning that the area under the curve represents 100% of the data. And it is completely defined by its mean and standard deviations. We should remember this from the last lesson where we talked about the empirical rule, how 68% of the data would lie one standard deviation away from the mean, and so on and so forth. We did with the empirical rule. And we'll be using that, but the empirical rule we were only able to calculate at these lines. Now, in this lesson, we will deal with data that falls in between one standard deviation or in between two standard deviations. So the z-score tells us how many standard deviations a particular piece of data lies from the mean in a normal distribution. And the formula for calculating the z-score is data minus mean in the numerator and standard deviation in the denominator. And if we were dealing with the entire population data, then our mu represents the mean and sigma represents the standard deviation. And if we're dealing with sample data, then x bar is the mean and s is the standard deviation. And these numbers may differ because the sample data is based on a small group that you have polled, and the population data is based on the entire group. So example 1, calculating z-scores. It says, given that the heights of Canadian women are normally distributed with a mean of 159.5 centimeters and a standard deviation of 7.1 centimeters, calculate the z-scores for the following pieces of data. Before I do that, just a recall. If we wanted to change these labels, we can. We can use the 159.5 for the mu. And then we would add 7.1 to get one standard deviation to the right, and that would give us 166.6. Or we can subtract 7.1, and that would give us one standard deviation to the left. That would be 152.4. And we can fill in this chart all the way if we wanted to. So right away, when we're looking at this, the first example, 148.2, we see is going to lie in between 1 and 2 standard deviations to the left of the mean. 160.3 would lie within 1 standard deviation to the right of the mean. So because of that, I expect this first z-score to be greater than, or I should say less than -1, because -1 would bring me to 154.4, -2 would bring me to 145.3. So I expect this answer to be between -1 and -2. This answer lies someplace here, so I expect it to be between 0 and 1. And this one's in meters, so we have to change to centimeters first, so we can apply it to our chart. Okay, so let's work these out. Here's our formula. I put the mean and standard deviation here for easy recall. And for part A, we're going to say that the z-score, and I'm going to list this in the subscript. So the z-score of 148.2 is equal to 148.2 minus 159.5 all over 7.1. And that's going to equal negative 1.59. And if we go back, I said it would be between negative 1 and negative 2. Negative 1.59 does fall in between there. For part B, we want to find the z-score of 160.3. So we put the data point in the numerator, 160.3. We subtract the mean, 159.5, and we put it over the standard deviation. And when we plug this into our calculator, we will get 0.11. Again, we said we expected it to be between 0 and 1, and 0.11 is between 0 and 1. So this next problem is written in meters. We have to convert to centimeters. So 1.7 meters is equal to 170 centimeters. And now we can find the z-score of 170. And that would give us an answer of 1.48. And again, that means that it would be between 1 and 2 standard deviations. Based on our chart here, we see that 170 falls in this region, and that's in between 1 and 2 standard deviations. So this chart is good for to let us get a ballpark, but now we can find the exact distance from the mean in terms of standard deviations. Now that we have z-scores, we can calculate the exact percentage of data that lies above or below that z-score. So here we have an example. Suppose that the average caloric intake for women is 2,050 calories per day with a standard deviation of 175 calories. If we assume that the caloric intake follows a normal distribution, find the percentage of females in your class that consume more than 2,000 calories per day. So 2,000 is the data point. More than tells us which way we're looking at the data. We're looking at 2,000 calories or more. 2,000 calories or more means everything shaded to the right of the normal distribution. So first, we want to calculate the z-score. We have the mean and we have the standard deviation. So we can say that the z-score of 2,000 calories is equal to 2,000 minus 2050 over 175. And that's equal to negative 50 over 175. And that is negative 0.2857. We usually round to the hundredths. So that's our z-score. So step 2 is to calculate the percentage, and that means to calculate the percentage of data that is more than 2,000 calories. So if we go back to our normal distribution, there is our mean. Here is negative 1 sigma, meaning 1 standard deviation to the left. And we see that this negative 0.29 is going to fall someplace over here. So someplace over here, but the more than tells us we want to shade everything to the right of the graph. So this is what we want to find, all of this data. Now, We know that from mu to the right is 50% of the data. So we need to figure out how much of the data is from mu to negative 0.29, and then we can add that to 50% of the data. So we've already done this part. Negative 0.29 was our z-score. And I've completed the chart here. We see that 2,000 calories is going to fall in this range here. That's where the negative 0.29 z-score will be. And here is the old school way of calculating percentages. So I'm just going to increase the size of this chart. We want to look for, in this is my x values or my z values for the z-score. We want to look for negative 0.2, and we see it's all the way down here at the bottom of the chart. And I've cropped that out in the next scene so we can see it easier. Negative 0.2, and then we want negative 0.29, so we're going to add 0.09 to it. So negative 0.2, we come all the way to here, and we see that's what we get. Now notice that this chart is telling us everything shaded to the left. Well, we don't want everything shaded to the left. That would be less than. That would be less than 2,000 calories per day. We want more than 2,000 calories per day. So if everything to the left is 0.3859, then how do we find everything to the right? Well, you have to recall that the area under the curve is 1. And if this shaded region is 0.3859, then the white region here, the non-shaded region, would be equal to 1 minus 0.3859. 1 minus 0.3859 gives us 61.41. 0.6141. When we multiply that by 100 to convert it to a percent, it's 61.41%. So that means that 61.41% of Canadian women consume 2,000 calories or more per day. Now we can also see how to perform this same task in a graphing calculator. Okay, so we just want to evaluate our z-score from the question that we're working on, and we were asked what percentage of data will have a z-score of negative 0.29 or greater. So on our calculators, we can hit the second key, the vars button, because above it in blue it says distribution, and we're going to choose the cumulative distribution function, the CDF, and we're going to enter in our lower bound and our upper bound. So since we want to know a z-score of 0.29 or greater, negative 0.29 or greater, we want our lower bound to be negative 0.29, and our upper bound, we're going to write 10 raised to the 99th power, and we can leave the mu at 0 and the standard deviation at 1, and hit paste, and now it has the function on our calculator. We can hit enter, and it gives us back the percentage as a decimal. So if we multiply this by 100, we end up getting 61.409%, and the answer was 61.409%. 0.41% because they rounded to the hundreds. So there I was using a TI graphing calculator to evaluate the same problem, and we saw that when we rounded to the hundreds place, we got the same answer, 61.41%. Okay, so here's another example. Uh, According to the Department of Health and Education, cholesterol levels are normally distributed. For men between 18 and 24 years, the mean is 178.1 and the standard deviation is 40.7. What percentage of men in this age range have a cholesterol level less than 239.15? So first we will find the z-score of 239.15, and then we will calculate the percent, but we have to go back and say what percentage of men in this age range have a cholesterol level less than? Our previous example with the calories was more than. More than shaded to the right, less than shades to the left. So we have to keep that in mind when we're doing the evaluating the percent. So we're converting our z-score, our data point into a z-score. So we have 239.15 minus 178.1 divided by 40.7. And we get 1.5 as our z-score. I've cropped out the part of the table where 1.5 shows up. Since it's 1.5 exactly, we use the column with 0. We're not adding any other decimals to it. And that tells me that 1.5, so that means that for our purposes, this line is z equal to 1.5, and everything to the left of that, less than, is 0.9332. Well, if we go back to our slide, we were interested in less than, so it means to the left. So there's our answer, 0.9332 times 100 gives us 93.32% of men between the ages 18 and 24 years old and those men have a cholesterol level less than 239.15. And again, you can solve this with the calculator also. And you see that when you round to the hundreds place, you would get 93.32%. Just going through the numbers that we plugged into the calculator here. With the normal CDF, you always have to put a lower level and an upper level. So because our upper level was 1.5, our lower level has to be negative infinity. But we don't have a negative infinity button on our calculators, so we type negative 10 raised to the 99th power. So my normal CDF is going from negative infinity to 1.5, and we just leave 0 as the mean and 1 as the standard deviation. If I go back to the previous example, because we were interested in shading to the right, we have our lower level as our z-score and our upper level as infinity. So we put positive 10 to the 99th power. So those are the only notation things we have to enter correctly with our calculators. But you have the chart, which I will upload a copy of this chart into Blackboard so that you can download it and use that to reference it. You can use the chart on a test. If you don't have a graphing calculator, if you do have a graphing calculator, you can use that on your test. All right, send me any questions through email, and your assignment will be posted in Blackboard.